All right, this is the third and last example of chapter 8.3. It is question 156. Let's read the question. Question 156. Suppose an electron travel at 6 multiplied by 10 to the power 7 meter per second through a distance of 0.2 meter from the start of the beam to a screen. Part A. What is the time of travel of an electron in the rest frame of the television set? Part B. What is the electron time of travel in its own rest frame? So, first part, we should write the information that we have here. So we are given the velocity. Now, by the way, even though we are not given the velocity in which frame, remember that the velocity has to be the same in all frame of reference. So this velocity is the same from the point of view of the electron, and it's the same from the point of view of someone outside the TV measuring how fast the electron is moving. Now, remember that the speed of light is 3 multiplied by 10 to the power 8 meter per second, which means that this velocity is 0.2 multiplied by the speed of light, okay? And as I mentioned before, it's simply more convenient to write it in that format. Now, the electron travel a distance of 0.2 meter. We will see in the next section that it's important that to notice that this distance is in the rest frame of reference. Okay, for now we don't pay too much attention, but we'll see that because of Einstein postulate, this is not the same in all frame of reference. For now, let's just keep it that way. So part A, we want to find the time the electron goes from being emitted to where it strikes the screen. Basically, distance is equal to velocity multiplied by the time. We got the distance, we got the velocity. So simply time is equal to distance divided by velocity, 0.2 divided by 0.2c, and we get 3.33 multiplied by 10 minus 9 second, or 3.33 nanosecond. All right. Part B, we are asked to find what is the time from the point of view of the electron. Now, remember, the electron is moving. Now, because it is moving from its point of view, the time will be less than when measured from an inertial frame of reference at rest. Okay, so the first part, we need to calculate gamma. In this case, it's simply one formula with one variable, and the variable is the velocity. We have it over here. We will find that the gamma is 1.02 in this case. All right. Now, at this point, it's simply plug and play. It's to find the delta T1. So delta T1 multiplied by gamma is equal to delta T2. The time we found here, it's important to notice it was measured from the rest frame of reference, which means it's the longer of the two time, which means it has to be delta T2. So in this case, delta T2 is equal to 3.33 nanosecond. So gamma, which is 1.02, multiplied by delta T1 is equal to 3.33 nanosecond. If we isolate delta T1, we get 3.26 nanosecond, or 3.26 multiplied by 10 minus 9 second. All right. So again, and this will be a theme in this chapter, it's always about finding which frame has which time. And as I'm repeating myself here, but it's important, the frame that is at rest always experience a longer time. So delta T2 is always our time at rest. Delta T1 is always the time in the frame moving. All right. So that's it for chapter 8.3. Let's go to chapter 8.4 now.